All right, so this is Julia for an entirely different field, operations research, linear optimization. So Miles and I are in the Operations Research Center here at MIT, and we do solve problems like this a lot. So linear programming, we have a decision variables x, which are generally continuous, but sometimes can be integers, and we want to maximize or minimize a linear function of these variables subject to a set of linear constraints. This is a pretty simple setup, but is widely used, like just in all these things you wouldn't even expect. Airline scheduling to production planning. I believe a text hyphenation algorithm uses it.
Like
yeah.
hyphenation uses a linear.
Yeah, it's a pretty complex optimization kind of setup they've got going. And of course, package manager for Julia has and may again in the future used linear programming. Yeah. The simplex algorithm, which is one of the ways we solve these linear programming problems, is pretty famous, and Iain called it one of the top 10 algorithms of the 20th century. And there's been speculation that since computers were created until sort of the 80s, it was basically consuming a large majority of the computer time available in the world solving these sorts of problems. So pretty important. How do you actually solve them? How do people solve these things in practice? Well, first of all, you've got to put it into the computer. So we have our mathematical statement of the problem, and then we use a modeling language to represent it. What we've got up there as an example is something called AMPL. And as you can see, it's quite human readable and closely resembles like the mathematical statement we might have. So the top line is our objective function, and the second one is a constraint on our decision variable as x. So this is what people use, AMPL, sometimes use GAMS, and these are commercial languages. They are specialized. They pretty much just do this, linear programming. And as a result, they're quite fast because they pretty much have to just do one thing, which is parse these sort of statements and turn them into a matrix, a sparse matrix representation. They have some like limited auxiliary sort of functionality that's usually pilfered from C, but it's kind of a weird mismatch and there's no consistent syntax, and they're not general purpose. On the other hand, we have open source modeling languages that are built on Python and MATLAB. So Pulp and Pyomo are obviously built on Python, and CVX and YAML are built on MATLAB. And they basically define objects or types to represent variables and constraints and so on, and use operator overloading to deliver the same functionality that AMPL might do by some sort of static text parsing kind of algorithm. The consequence of this operator overloading is that they're generally quite slow. They have a lot of temporary objects that get created, and there's a lot of thrashing. So they're nowhere near as fast as the commercial languages.
Quick question about AMPL, since I don't really know it.
Sure.
Suppose you actually have heard of the dot product. Can you replace that line with something more vector-like, or must you use that sort of scalar kind of? You
have to use that. But I mean, internally it is effectively doing.
Right. Internally, yes, but as a means of expression,
no, there's no.
95% of the population doesn't think that way. Maybe that's fine.
This is a very special purpose language.
Yeah.
You just write that.
You just write that. Okay.
Sometimes the statements can get more complicated. For example, profit might not be just an index into an array. It might actually be an expression that depends on the index, so a dot product. This is basically the level of generality they're decided on, and it's sort of conventional. Yes, so specialized, fast, but not general purpose, open source, slower, but you've got all the magic that comes with using Python or MATLAB. So we thought, aha, Julia, domain-specific languages, we can do everything, right? We basically thought Julia would be a good contender to do this, and it's basically the macro functionality that lets us get the speed of AMPL, but with still retaining all the general purpose functionality you expect from Python or MATLAB. So this is an example of JOLP, Julia for Linear Programming, and this is the same model we were building in the previous example, but now in Julia. We define types like model and variable, affine expression, constraint, and use this macro. Before we had sum over j equals 1 to n. Now we have some expression, this for j equals 1 to n. And as you can see, it's quite readable, and someone who was used to AMPL wouldn't be frightened too much by this. But it's very quick, and the reason why is this SumExpression macro and similar macros we have built in. It's quite simple, really. It takes this expression, ci times xi for I equals 1 to n, and pulls out this AST we were talking about before, and pulls out the fact that the left part is the values you're multiplying by, and the x is the variables, and reassembles it into two arrays, the coefficients and the variables. And that's how we store these affine expressions as sparse rows. This works very well. So we basically generated some instances from a general class of problems and tested them for different sizes. We've just shown two large problems here to really show how it kicks in. AMPL can take these large models and output a sparse representation of them in 4 or 6 seconds. Julia is only a little bit behind, but it might look not so fantastic. But when you compare to the alternatives now, such as Pulp, which we ran in Python and in PyPy, which is the just-in-time compiled version of Python, we're beating it by a large amount. And compared to Python, it's not even really worth talking about. So the reason this is important is because you hear operations research people talking about, oh, I might experiment in Python, but if I really want to implement my model for production usage, I have to switch to C or C++ and use these really nasty. It's nasty doing this kind of stuff in C and C++. It's obviously not designed for it. Now they could use Julia the whole way through from design to production because it's got the speed you'd expect and require. And so we think that's pretty exciting, and we hope it just gets picked up by the community. So I'll hand over to Miles. One thing.
You should say that it's not ready yet.
Oh, and it's not quite ready yet for use, but we're getting there, and we'll release it as a package when it's done.
So a question about what this is benchmarking. Is this benchmarking solving the actual problem?
No, not solving.
This is
parsing.
Parsing.
So
Parsing and writing out.
Parsing and writing to file.
Right.
So there's on the order of like 10 million variables in these things. So there's a lot. That's 10 million objects at least. There's 10 million variable objects somewhere in there. So there's a lot going on.
Does it take this little expression and generate an actual matrix? Or?
Eventually, yeah. So basically, in the meantime, it stores rows because it's all unfortunately, like the representation is that the mathematical representation is row-wise, but you ultimately need a column-wise representation of it. So we basically store these rows. This is basically, that is a sparse row. It's the coefficients and the variables you can think of as the columns of the sparse matrix. And then at the end, we basically flip it. But this is the intermediate format we store it in.
Where do you see, is it in writing the file that we're slow compared to AMPL, or do you have any guesses?
It was, but we've basically tweaked it and
that was yesterday.
we've fixed mistakes and things.
Well, the two components of the time are just building a model in memory and then writing the file. So writing the file is maybe more than half the time.
Yeah, writing to a file is expensive, but on the other hand, AMPL also has to write to file. So as long as Julia's file I/O is efficient, that's not like the binding problem. AMPL has an advantage because it's like a static text analyzer. It can like parse it like using like Yak or whatever. Like it can actually analyze it statically, whereas we're sort of in a dynamic programming environment. So we can't ever. It's not really reasonable to expect we can ever fully reach the same speed. But we basically cut out all the inefficiencies using.
So asynchronous writing, like as you're building it and you keep writing, is that something that would help? You
can't write until you're done because
you're going to transport.
You have to turn it into a column representation, which is what is used by solvers. Unfortunately, that'd be cool though. If you could.
How much time is the actual solving relatively? Just to get an idea, like if you're doing the two.
It depends. It can depend wildly. I mean.
But like for these 5,000, 10,000 examples.
It would take. It could take 20, 30, 40 seconds. So at this sort of speed level, it's like, okay, that's fine, I can deal with that. If it's taking 200 seconds, you're spending more time building the model than solving it, which is why people don't want to use these in production, because it seems like a waste of time when you could just be focusing on solving it. Yeah. Any other questions? Okay.
Linear programs like always use like this kind of an interface Is that quite common, or?
Yeah. Because the only alternative is to like actually make the sparse representation of the.
But people don't do that. I mean, that's what I would have done.
Well,
I've done that. People do that, but
People do
it takes a lot of time, and it's easy to make mistakes that take
Okay.
It's completely
hours
unmaintainable, of
yeah.
course,
I
because
see.
there's no intuition to it, and yeah. They're also highly sparse, like usually like very, very sparse.
I'm a little, I don't quite understand yet how it's reading in. What's the representation externally? Does it have like long coefficient vectors,
Oh.
CIs and so forth?
Yeah, so here we just generated, as an example, 2 arrays. These would obviously
Yeah.
have some meaning, but we just, as to demonstrate.
Yeah.
Yeah, so they're float arrays. They have a data that's maybe come from an external file or something, and yeah.
But I don't quite understand what the model and the variable functions are doing.
So they're types. They're like objects we're creating to represent the model being the whole thing, and
Variable variable really just stores an index, a column index. That's all it is.
and bound.
Yeah.
The variable is probably mostly for overloading the star operator, right? So that you can.
Right. So
put it in the
initially
function.
we did an operator overloading implementation, and then we figured out that we needed to use the macro.
Yeah. Operator overloading didn't like really help us beat the other languages, but the macros take us to that point. Because if you use operator overloading, there's like a lot of temporary allocation of objects,
Right.
and it's really just
I guess the point is really that we have all these different things in the language, and sort of you're able to find one that met your performance
Yeah.
goals.
Yeah.
yeah, macros. They're blazingly fast. Like there's pretty much nothing better you can do than this, I guess, because it directly builds from the natural representation to the most efficient
Yeah,
storage.
I mean, we do need to do some more work on making the macro. I mean, right now, macro is not too flexible. It needs that exact syntax.
Yeah.
So it's interesting how you don't have a dummy variable and you just put it in just so you can remove it later, right? Because the x's are like dummy variables, right?
What? No, they're the decision variables. So this is like a knapsack problem we've got here. Although, yeah, we've got a profit. So we're taking items that have a certain profit associated with them. We're trying to fit them inside.
But I claim at this point, x is like
But
it's not serving any purpose. other than
when
talking to
when you have a
people.
sparse model, you're not going to sum over all of the x's. In that case, you store it like a sparse row with the
Well,
indices and the
J-
coefficients.
all right, it's probably how you think about it, but the J indexing would sort of accomplish that, not the X either.
But what typically you do is, if you have different variables to represent different things, you can have different arrays. You're not going to have all of the variables in one array. You can do different arrays and index them like that so that they have a meaning.
Still dummy variable, all right, there anyway, but
it-
maybe nice
Kind of the whole
documentation.
reason this language like AMPL exists is just because people want to think of it that way.
Yeah, that's what I'm sure, yeah.
Yeah, I mean, you could use raw column indices, but you'd lose the whole maintainability that we're sort of trying to strive for.
You could probably even try to do something with data frames, but maybe that's combining two worlds too quickly, because they also have labels.
But this is really, the real important thing is that everything is expressed as a sparse. All the constraints are expressed as sparse vectors.
Okay.
Okay, so the next part of linear programming is actually solving the problems. The simplex method, which we mentioned, there are other methods, but this is, I'd say, still the most commonly used one in practice. And it's also really hard to implement. It could take, I mean, it's about the work of a PhD thesis. That's what it takes to write a good implementation from scratch.
Is that your PhD thesis?
No, no. But I've seen a couple.
Yeah, and quite recently, even like 2007.
2007,
someone
there was
basically
one.
spent their whole PhD making a state-of-the-art, incorporating all the tricks, all the linear algebra tricks, all the algorithmic tricks. Yeah.
What happens
yeah.
to those implementations typically?
So I think that's some of them are open source. There are high quality open source implementations. So at this point, there's no practical reason to rewrite it. But so that thesis in 2007, basically, from the 80s to until then, there was really no documentation of all the tricks that went into it. So that was the contribution of that thesis.
Just to bring them all together into one body of code.
Yeah.
Is there a name? How do we find it?
Koberstein?
Is that at MIT or?
No, it was in Germany.
Okay.
So it's both algorithmically challenging and computationally challenging. The computational challenges are it's not naturally vectorizable. An efficient implementation, it's entirely sparse linear algebra, and not black box sparse linear algebra. You have to write it all yourself. And that leads to being memory bound. So there's really a lot of cache misses. It tests the language in ways that other algorithms don't really push the language. So MATLAB implementations, I don't know of any one that people use in practice because it's just too slow. So the question is, can Julia compete with what's out there? So I put together some benchmarks of a few important operations, not all, but I think enough to make a convincing case. The first is a sparse matrix times a sparse vector product. Second is scanning a sparse vector. And the third is sparse AXPY, that's the BLAS syntax, so adding a sparse vector update with some additional if conditions on each iteration. So here we have times Julia, C++, C++ with bounds checking, MATLAB, PyPy, and Python. And the execution times are relative to C++ with bounds checking. And Julia is pretty much right there where it should be. Compared to the benchmarks that are on the Julia website, it's all less than factor 2. Maybe the bounds checking is an issue that would have to be worked around. I don't know.
Yeah, that's definitely part of it.
Yeah.
Yeah, we've had some discussions to figure out how to get rid of bounds checking overhead and critical things like this.
Yeah. So Julia is within a factor of 2. MATLAB is kind of not really consistent, but around the factor of 10. PyPy is around the same as MATLAB, and Python is just far out there.
One of the interesting things about this is that of all the convenient things you get from higher level languages like bounds checking, not all of them are that expensive. Like bounds checking is actually not very expensive, which is sort of interesting to observe.
Yeah.
Is the Python implementation using NumPy or just plain Python?
It's plain Python because there's nothing you can do with NumPy. It's all you have to write it yourself. Write it using your own loops.
And there's no word for this in SciPy notes.
No, I mean I can show you what the actual operations.
I think SciPy might have like the sparse matrix, sparse vector, but
I don't think so.
they don't have it.
I mean the most common is sparse matrix times dense vector. That's all over the place. But sparse matrix times sparse vector is really a specialized operation. Let's see if this
Well,
works.
and they could have it, but they would just call the C implementation.
In Julia, are you calling the inbuilt one, or are you writing your own?
I wrote my own.
Okay.
Yeah, this is all from scratch.
So you should just send it back so that we can incorporate it.
But so the another thing is that the sparse vectors
Oh, it's a special form.
need to use a special format to store the sparse vectors.
Okay.
But So this is this is the sparse matrix sparse vector product. You're looping. So the way to see that, think of a sparse matrix sparse vector product is thinking of the matrix vector multiplication as taking a linear combination of the columns, and that way you only need to loop through the non-zero elements in the vector. So the outer loop is looping through the non-zero vectors, non-zero elements of the vector, then looping through the columns of the matrix, adding the column to the output. So really low level, something you would normally write in C. It's in Julia now. I think that's, unless you want to see more.
So this isn't the kind of calculation where you know ahead of time the sparsity pattern and the result?
No, the sparsity pattern changes every time.
Okay.
So I think this makes the case that you could write a pretty fast simplex algorithm in Julia. I'm not planning on spending my PhD thesis on it, but.
But given that there is a PhD thesis out there, and one just were to try to translate it
Yeah.
from scratch, wouldn't it be a much easier test? I mean,
Yeah,
no longer a PhD thesis.
It's not a PhD thesis, maybe.
A master's thesis. I'm not sure.
It's still a few months, or.
Okay, so
yeah.
it's like a master's thesis.
Yeah.
I would
yeah.
point out too that factor of 2, we're not planning on being like, we want to close that. Like, that's not permanent. But there's just other fish to fry in the meantime. But
No factor of 2 left untouched.
Yeah,
Left behind.
exactly. Eventually Jeff will have nothing else to do, and he'll spend a couple of months to get all of those numbers later.
And nowadays if we see something that's over a factor of 2, then we try to do something about it. If it's under a factor of 2, then we kind of punt it to later. But the goal is not to be within always a factor of 2.
And it was reassuring, like nothing special is done in that code, right? There's no unintuitive. We just wrote it
No
like
tricks.
you'd wrote it like you would write it, like so. It was reassuring to see we got that performance without having to cheat. Like it's just done and out of the box.
Maybe I'll just mention one performance thing. Something I had to do was to, if you use the dot operator inside a loop, I think it has to evaluate that every time.
It does.
Yeah,
It does, yes.
Factor,
Yeah. So what I had to do was just get a reference to the arrays outside the loop.
Fix that, yeah.
It's a pretty small thing that you can probably fix. But that's really the only thing I had to change.
Even if you look at all the code in the sparse matrix implementation, it always does that, so that it's never doing it within a loop.
Yeah.
Just as good practice.
Well,
A good practice for.
it would be nice if we just fixed that overhead. Yes.
Yeah, it would be nice if it just worked.
Okay. So on top of that, I have a tutorial that's almost entirely unrelated to what we've been talking about on implementing a parallel asynchronous optimization algorithm in Julia. It doesn't require a background in optimization. I think it's a pretty good tutorial on getting remote references, remote function calls, and even doing some asynchronous work and seeing how that works in Julia. So if you want to take a look, go ahead.
Same site as yesterday. That's where all the codes are.
Did you want to say 1 or 2 words? I mean, it really does exercise parallelism very
Okay.
well. Just like, say from even if you never were into optimization, say what Julia brings you learn.
Let's see. So there's I'll skip this stuff. And maybe it's better to look at the code and see what's going on. So at the high level, you have at the high level, the first version is you really just have a map that you want to parallelize. And the map is evaluating some function that we're going to make difficult by calling sleep inside it. But in real, there are plenty of applications where, I mean, it's not too arbitrary to do that. It's kind of reasonable. So what you have is you're calling a bunch of parallel map. You get the results. You process it. You solve some optimization problem, and it's in a loop until you converge. I think the fun part is doing a bit asynchronous. Is you can rewrite the optimization algorithm so that it can keep going when it just gets a proportion of the calls back. You can keep running the algorithm, and that turns it into an asynchronous sort of a master worker type algorithm. And the whole implementation is on the screen right there. So it'd be something maybe fun to play around with.